Hi students. So as we have discussed in the previous class, we have discussed about inner product spaces and its theorem. So we can solve the problem using this one. Okay. So now let x be 2 comma 1 plus I comma I and y be 2 comma 2 minus I comma 2 comma 1 plus 2I. So now we have to compute 2 plus I, right? So now what you are you have to compute x comma y. So that is inner product x comma y. So it is very simple. Let x, what is given, 2 comma 1 plus I comma I, and y is given as 2 minus I comma 2 comma 1 plus 2I. So now we have to find the inner product of this one, x comma y equal to what you have to do. So 2 comma 2 minus I the whole bar. So what we are going to get is 2 comma 2 minus I the whole bar. X comma y dana. So you have to consider that one, 2 into 2 comma minus the whole bar. Next one, 1 plus I minus 2 the whole bar. Okay. So 1 plus I into 2 the whole bar plus I into 1 plus 2I the whole bar. Okay. That's all. So we have to if it is this one, we have to calculate and we have to get the real part of this one. So you have to, if it is integral, if it is the whole bar, the imaginary part, if it is minus, then it becomes plus, and if it is plus, it becomes minus, right? So 2 comma it becomes 2 plus I. Okay. So this becomes 2 comma 2 plus I plus 1 plus I, there is no change. So there is 2 bar, this is the real part. If you conjugate that one, we won't get that one. So we will get the same answer as 2. Then I into, so if we do this one, we will get it as 1 minus 2I. So we have to multiply this one, 4 plus 2I plus 2 plus 2I plus I into I is I minus 2I square. So 2I square is, I square value is minus 1. So totally we will get the value as 4 plus, already 4 plus 2 6, 6 plus 4I becomes 5I, right? So 6 plus 5I minus of 2 into minus 1, 2 into minus 1, that is plus 2. So totally we will get the value as 8 plus 5I. Okay. So this is the problem. I think you understood this one. So x, this is y, then you have to correlate that with respect to inner product, means 2 comma 2 minus I the whole bar, I plus that one. So y term becomes 2 the bar, you have to take the bar for that one. Okay. So this is the problem which we have discussed. Next we are going to the problem, next one. So next one is the problem, show that a comma b comma c comma d equal to ac minus bd. So on R2, that is basis, right? So dimensional basis R2 is not inner product space. We have to consider that one as, not an inner product space, right? So now we are moving on to this one. What is given? Given another one concept of a comma b. This is one part. This is one x. We have to consider this x, right? Then c comma d. So this consider this as y. Okay. So we can consider. You have to consider like this. So its whole answer is ac minus bd. So you have to show that this is inner product or not. Okay. So it is given that R2 is not an inner product. So we have to do according to that. So if it is not inner product, means it should satisfy every properties, right? So it should satisfy every property which related to us. So that property is we have the three properties, that f1 x comma x plus y. We can consider anything. So x plus y comma z equal to x comma z plus y comma z, and then x comma y the whole bar equal to y comma z. So y comma x, and then another one x comma f comma f, or otherwise x comma x is equal to as greater than 0 if and only if x is not equal to 0, right? So these three conditions we need. Okay. So now we are moving on to this one. We have to consider this as ab equal to 0 comma 1. So consider ab as 0 comma 1. Okay. So and BC also like that we have to consider, and we have to go for this one. So this is in R2. So this is basis of R2, right? So now we are moving on to this one. Consider this process. Consider this process, and we have to check whether it is not, it is an inner product or not. Okay. So now we are considering 0, 1, 0, 1. Okay. So we have to consider both the things. So if it is 0, 1, 0, 1, that is also same one. Okay. So we have to check everything, right? So one property is that is x plus y comma z equal to that one. Okay. Another one is x comma y equal to x comma y the whole bar equal to y comma x. Another one is x comma x, right, should be greater than 0. So now we have to consider that one. We are considering this as x. So already we have considered this as 1. 0, 1 belongs to R2, right? So that is R2 in basis, right? It is not 0, 0. It should not be a 0. If it is 0, 1, that is different from 0, 0. Okay, it is not whole 0. It is different. Okay, so it is different. So you have to consider this as this one x, and that is different. We are considering that as 0, 1. A comma b we are considering that as 0, 1, that is different from this one. So we have to go for that one. Okay, so now we have this formula, right? AC minus BD. So AC minus BD, AC minus BD, right? This is A, this is B, this is C, this is D. You have to consider like this. So here we are considering like that, but from the defined one in the problem, we are considering like this. Okay, so here A is 0. A, C, right? C is 0, 0 into 0 minus B is 1 and D is 1, 1 into 1. So totally we are getting it as minus 1. So it is not equal to 0. Okay. So its answer should be greater than 0, right? So it is minus 1 is not greater than 0, right? Your property, third property is that one, main property is that one, it should be greater than 0. If it is equal to 0 also we can consider a little bit, but if it is minus 1 we should not get that one. So we should totally neglect that one. So it is not given as 0, 1. It is not given in the problem that it is 0, 1. We can consider anything which is real part, right? So if we are considering in 0, 1 itself, it is not getting. So therefore the space is not an inner product space, right? So therefore this is not an, R2 is not an inner product space. Okay. So next one, I think you can view the questions. Can you able to view the question? So we have seen this problem, right? So next we are going to moving on to show that the vector space H with dot comma dot. So dot is the main thing here. So dot defined on 0, 2, 5. So this is defined as 0, f inner product f comma g is 1 by 2 by 0, 2 pi f of t g of t the whole bar dt is an inner product. So we have to solve that is an inner product or not. Okay, third one we have given, what is given, f comma g, inner product f comma g is this one, 1 by 2 pi 0 to 2 pi, I think, yes, 0 to 2 pi f of t g of t the whole bar into dt. So we have to go that it is in the interval 0, 2 pi. It is in the closed interval 0, 2 pi. It should not go beyond that. Okay. So now we have to prove the three things. So it is not in one property. We have to prove that in three ways of things. Okay. So first one, you have to consider that as. So first to prove first property. So if we prove the three things, then we can say that it is an H is also, it is given that H defined on this one is an inner product or not. Okay, if it is, if we have to prove H is inner product, wait, H is inner product, first of all we have to prove one property, product space then we have to consider first one to prove first property. So that is consider f1 plus f2 comma g equal to f1 comma g plus f2 comma g. Okay, so first property is this one, so we have to go move according to that, we have to get this one. Okay, so with this one consider this as like this. Okay, so now f1 plus f2 comma g equal to, so we have to define according to this one, so we have to get like this one, so the defined thing is this one, so we have to go according to the defined one which is given, so and then at last you have to get like this. Okay, so now 1 by 2 pi 0 to 2 pi, instead of this one we have to write it as f1 of t plus f2 of t into g of t the whole bar into dt, right. So now we have to split it 1 by 2 pi 0 to 2 pi so 1 by 2 pi 0 comma 2 pi, you have to split that one, f1 of t into g of t the whole bar plus f2 of t into g of t whole bar into dt. So we have to split that one and we have to write separately we have to write 0 comma 2 pi f1 of t g of t the whole bar into dt plus 1 by 2 pi integral 0 to 2 pi f2 of t g of t whole bar into dt. So we have to write this one as we have to write like this one, so we have to write like this one, instead of same this one we have to write that as f1 comma g plus f2 comma g. So are we getting like this? Yes. So next one, second condition is that to prove f comma g the whole bar equal to g comma f, we can write either this one or that one, anything else we can write. Okay, this is up to us. So if we are going to f by g the whole bar, we have to prove this one, so we have the definition, we have to put the whole bar for this one. Okay, so that is 1 by 2 pi integral 0 to 2 pi f of t into g of t the whole bar, g of t the bar, this is this one for this one, right. So it is f comma g the whole bar is given for this one, so we have to apply this one and we have to get that one. Okay, so this is equal to 1 by 2 pi integral 0 to 2 pi, this we will get it as g of t into f of t the whole bar, because 2 bar the whole, if it is a bar the whole bar is nothing but a. Okay, if it is a bar then it is a bar only, if it is a bar the whole bar, if we take another one we will get a. Okay, desired a, so with that we will be getting f of t the whole bar equal to f of t the whole bar, f of t bar, then g of t the bar the whole bar. So 2 bars are there, so if we cancel that one we will get g of t. Okay, next with that we can rearrange and we can write it as g comma f, that's all. So this is proved. Then next one, third condition, we have to get f comma f should be greater than 0, right. So now we are moving on to this one, greater than, it may be greater than or equal to anything else. So if it is equal to 0 also we may consider. Okay, so now we must move on to this one. Okay, now f comma f equal to 1 by 2 pi integral 0 to 2 pi f of t into f of t the whole bar into dt. So here it is f comma g. So since it is f comma g, we are getting f of t into g of t the whole bar into dt. Here it is f comma f. is equal to 1 by 2 pi 0 comma 2 pi f of t into f of t the whole bar. Okay. So therefore we will be getting f of t into f of t the whole bar can be written as modulus f of t the whole square into dt. Okay. So this is always be greater than 0, greater than or equal to 0. So therefore this is always be greater than or equal to 0. So it is proved that f comma f should be greater than or equal to 0. It may be 0. If it is 0, then we can get that is 0. So if it is greater than 1, we will get it is greater than 0. Okay. So we are getting the three things, this one and this one and this one. So therefore we can say that H, that is H which is given as Hilbert space, right? H is also an inner product space. Inner product space. That's all.